Alright, hello and welcome back to the ongoing lecture series on halftone reproduction from pre-press repro techniques. So, in the in the previous lecture that we had started, I think we had completed around three lectures in PPRT. So, we had talked in the first lecture about what is the difference between continuous tone and line tone and halftone reproduction, what are some of the features of halftone reproduction, how it is done, and in the last lecture, that is the previous lecture, we had talked about different types of halftone screens that we normally use during halftone reproduction through conventional method using a process camera. Now, in this particular lecture, we will be starting our discussion. Our this lecture is will be mainly focused on the three theories of halftone reproduction. But before we can talk, in detail about the theories of halftone reproduction, I thought I would just give you some brief idea about some of the terminology that you should, I think, know uh, before we can actually um, begin with this conversation of different types of theories of halftone reproduction. All right. So let us begin our conversation with a little bit background on optics. I think this is, I don't need to go back to your school level optics and teach you what will be the where the image will be formed if the light ray is parallel or if the object is placed in the R or 2R or F, whatever. That is, I don't need to do that, all that. That is, you've already done in the school level, right? In this particular lecture, I will be talking about specific terminologies. All right, starting with the term known as F number. Hmm. F number, very important term. Like F number is basically one term that we normally use in photography, but you will find out a analogous term known as the V ratio, what we refer to as the V ratio. In we write in the convention of writing F number is like this. So F1, F2, like this. All right. So similarly, V ratio can be written as like this. Okay, so this is just the nomenclature and the methodology of writing all this, V ratio, F number, and all this. That is not really a big deal. But let us now understand what this F number is all about. F number, if we can mathematically define F number for an optical system, we say that F number is basically the ratio between the focal length of the optical system to the diameter of the lens. Okay, just to give you a very brief review, what is the focal length of a, let us say, a convex lens? So this is a convex lens, right? This is the optical axis, right? Pardon my drawing, you all know that I cannot draw properly. Now a light ray which is passing or hitting the convex lens or lens parallel to the optical axis shall cross the lens and pass along a point on the other side, and that point is known as the uh, focus for that particular lens. Or simply we can say any line or any light which is passing parallel to the optical axis will meet at a point after getting refracted through the lens. That point is known as the focus of that particular optical system. This is for convex systems. For concave systems, it will appear the point from which the light rays traveling parallel to the optical axis will appear to diverge from that particular point is known as the focus for the concave system, and for convex system it is the point at which parallel lines after getting refracted by the lens will appear to converge at. Okay, so that is why it is also convex lens is also known as converging lens and concave lens is also known as diverging lens, right? So this is just a brief review of what the focus is. So the focal length will be this much on either side, right? Now what is the diameter of the lens? This one, So if it's a circular lens, then the diameter of that opening through which light can pass, that is the diameter of the lens, which we also call as the lens aperture. There is another term which is known as lens aperture. So now we will not say diameter all the time. We will say lens aperture. That is a more acceptable term in this optical field, at least in process camera. So F number is basically, you will understand. Right now you may not understand why I am talking before beginning with the theories. I am talking about a lot of terminology, lot of new terms and equations and all. But later on you will understand the significance of all this. All right. Now see. So what is the meaning? So what is the significance of F number? If I ask you what is the significance of F number? Now normally in cameras, what we see, the F numbers are discrete levels. You know what is the difference between discrete and continuous? So one value of F number may be 22. The normal convention is F by 22 is written. So the F number is 22. You do not say F by 22. You say F number is 22. 22 F number. Alright. So the F number is basically given in some discrete steps. Alright. Like F may be 22, it may be 16, 11, etc. So for in our process camera also, it may be 32, 64, 120, like that. Now these are basically discrete. There may be some fractional F numbers also, but these F numbers normally in any optical system, they are discrete in nature. So it cannot be the F number cannot be 22.1, 22.2, 22.3, etc. So it will either be 22, then the next F number will be 16. So what is the meaning of this? We say that whenever we are changing the F number, we are changing the stop. Basically it is said that we are changing the stop. So we are adding one stop. Adding, I mean, if you go on, increasing the number of stops, that can mean different things. Increasing or decreasing the number of stops can mean different things. Even the term stop in optics, especially in photography optics, can mean a lot of things. So it can mean the exposure time, it can mean the F number. All right. So depending on whatever you are using, whatever parameter you are changing in the optical system, the meaning of stop will change. So in this scale that I have shown in front of you over here, you see the first F number is 22, then is 16, 11, etc. So what is the meaning of all these numbers? What is the meaning if the F number is decreasing for the optical system? What will be its physical significance during photography? The physical significance is that, see, the ratio of the your focal length and the diameter, that means aperture. Aperture is the F number. So I mean the ratio between the focal length and the aperture is the F number. Now if this ratio, if this fraction basically is increasing, then which value is increasing? Which value may increase or decrease? Tell me. Now see, focal length normally remains the same. So for example, for an optical system, focal length will normally remain the same. If we are talking about a singular optical system, the focal length remains the same. But so if this remains constant, right, then what will be the variable condition? The diameter or the lens aperture will be variable. Lens aperture is also the meaning of lens aperture can also, you can say, it is basically you can say it's an opening, lens opening. So lens opening will control how much amount of light is entering through the lens into the optical system. So if you are increasing the D value over here, if you are increasing D, that means you are allowing more amount of light to enter into the camera. Am I right? So if in this ratio, the denominator, D is the diameter, is also the denominator in this equation. So if the denominator of any fraction increases, does the fraction increase or decrease? It decreases, right? That means what? When the F number, that means as we progressively go on in decreasing the F number, that means we are basically increasing the lens aperture. We are allowing greater amount of light to enter into our optical system, right? Basically what we see is when we change from one F number to the next F number, one level of F number to the next level of F number, we say that we change the F number by one stop. right? Where we may be either increasing the stop or decreasing the stop. So when we are decreasing or adding one stop basically, decreasing the stop basically, then the f number is basically reducing, and if the f number is reducing, that means it will allow more light to enter into the camera, right? So what effect of all this is happening, that later on when we'll talk about the theories of halftone photography, then you will be able to understand all this. But normally when you see greater amount of light enters into the camera, then there is a chance of overexposure. Now you tell me, under what circumstance do I want overexposure, or when in under what which scenario I want that the imaging situation, in that while imaging I want extra amount of light or more light to enter into the optical system of the camera, when we are basically shooting something which in itself, the original itself is devoid of large amount of light. So maybe a night time, we are shooting something in the night time, or we are shooting a original, we are recreating in a process camera terms, we are duplicating a original which has greater amount of shadow than it has amount of highlight, so that we call as low key image, that we call as low key image. An image having greater amount of shadow area than the highlight area, that is basically known as the low key image. So getting duplicates, creating duplicates of low key originals requires a lower f number. So in that terms, in process camera terms, we will not use the term f number anymore, we'll use some other, that is the V ratio. Instead of f number, we'll use the term V ratio. So it basically means the same only, the ratio remains the same. In case of the ratio here, f number ratio means ratio between the focal length of the lens to the diameter of the aperture. So in that process camera terms also, we'll see the V ratio is ratio between the camera extension to the your lens aperture basically. All right, so this is one thing. Now so if decreasing the f number increases the size of the aperture, increases the diameter, allowing more amount of light to pass into the optical system, definitely increasing the f number will do just the reverse of it. So we'll do it when the image area is high key image, we are reproducing a high key image, or during daytime when the amount of light is very high. During that time, this type of f number we can basically use, higher f numbers we can use, so in order to lower the amount of light that is entering into the optical system, right? Now basically regarding the stop, I would also like to state that stops are also unit which is used to quantify ratios of light or exposure. So like I said in the beginning only, so stop can have multiple meanings here. So in this context, I am saying that here adding one stop is basically increasing the amount of light entering by decreasing the f number. But in another term also, it can also mean the exposure time, for how much amount of time. Normally what happens, these are not very discrete. If you have basically automated your operation, if you have automated these f numbers, exposure values, and this exposure times and all, then what is going to happen, if you decrease the f number, then the exposure time will also decrease. Why? Because normally you see, decreasing f number means what? Decreasing f number means widening the aperture, allowing more amount of light to in order to compensate for the extra amount of light that is hitting onto the film. What is done, the automatically the camera will compensate for that by reducing the exposure time by half. So it is actually, whenever you see the exposure values are that is also known as stop basically. So each stop is marked with its corresponding f number and represents a halving of the light intensity from the previous stop, that I have already told. This corresponds to a decrease of the pupil and the aperture diameter by a factor of 1 by root 2. So if you consider, if you find out the values, you will see that from one stop to the other, if you decrease the stop, then the value f number is also decreasing by 1 by root 2 of a value, right? Now as I was saying, that in case of your exposure time, this also is controlled. Stop in other term is also related to the term of shutter speed. So depending upon your f number, you can automatically control the shutter speed also, because you see opening up a lens by one stop allows twice as much as light entering the lens and hitting into the film. Therefore, to have the same exposure at this larger aperture, we need to reduce the shutter opening time by half. So, if your amount of light entering into the optical system is doubling, that means in order to compensate for that, in order to remain the keep the exposure value at the same rate, then what you have to do, you have to reduce the exposure time or the shutter speed, basically how much amount of time the shutter is basically open, you have to reduce that time by half. So the film will respond equally to these equal amounts of light, since it has the property of reciprocity. This is less true for extremely long or short exposures, where if we have reciprocity failure. Aperture speed, shutter speed and film sensitivity, which I have already told in the first lecture on film photography, that was related to film speed, depending on what type of characteristic curve you are using for the film, what type of silver halide you are using for the film speed will change. If the film is of high speed, that means it is going to get developed within a very short amount of time and with a very little amount of exposure. So all these things are basically interrelated, but here the reason I told you about all this is just keep this in mind, the point regarding f number and v ratio. So it is basically analogous to each other. In process camera terms, we use the term v ratio instead of f number, but mathematically and even physically, they represent the same concept basically. So when you decrease the f number or v ratio, this means that you are actually increasing the amount of light entering into the optical system. So the chances of the film getting overexposed increases. In order to compensate for that, you need to lower the or you need to not lower but increase the shutter speed. That means lower the amount of time for which the shutter is basically open. So quicker the shutter closes, then lesser amount of light will enter into the optical system and finally reach into the film, and thereby the amount of exposure level will remain the same. All right, so this is about the f number. Next another important term, which is known as the depth of field. Now depth of field is mathematically represented as this one. So for cameras that can only focus on one object distance at a time, depth of field is the distance between the nearest and the farthest objects that are in acceptable range of focus. Now, acceptable focus or sharp focus is defined as a property called the circle of confusion. So, I will be talking about circle of confusion in the next slide. The depth of field can be determined by focal length, distance to subject, the acceptable circle of confusion size, and aperture. Right now, here in the formula that you are seeing in front of you, here C is basically, C over here is representing the circle of confusion. Circle of confusion is basically the the diameter. Basically, I'll tell what circle of confusion is. F is basically your focal length. N is basically your f number, and distance to the subject from your lens or the camera is basically represented as U. As the distance or the size of the acceptable circle of confusion increases, the depth of field increases. Because as you can see that circle of confusion is directly proportional to depth of field. So when the circle of confusion increases, depth of field increases. And also as the the regarding the depth of field changes linearly with f number and circle of confusion, but changes in proportional to the square of the focal length, as you can see, and the distance to the subject. So what interesting thing that you might consider over here is that, so it is basically DOF, I mean depth of field is inversely proportional to the focal length. However, what is most interesting to notice over here is that DOF is directly proportional to the f number. That means when the f number increases, the depth of field increases. With the help of the image that I have presented in front of you, you see when the f number was 1.4. So I already told you that f number can be fractional, but it cannot be irrational. I mean, it cannot be 1.4, 1.41, 1.42, 1.43, not like that. There are specific values of f number, and how is it controlled or how is it determined? From one stop to the other, the f numbers will either increase or decrease by a factor of 1 by root 2, right? Now, one from this equation, that is DOF is approximately equal to 2u square nc over f square, where u is the distance from the object of the camera or the lens, n is the depth, f number, c is the circle of confusion, f is your focal length of the lens. If the we can see from here that DOF is directly proportional to the f number. That means when f number increases, depth of field increases. See, this is an image. Depth of in very simple terms, you can express depth of field as at how much amount of what to say, horizontal distance can your camera capture without blurring out the farthest objects. That is basically your depth of field. Now, in this first case, you see, when we are using an aperture of having an f number of 1.4, which is a very low f number, that means the aperture is very wide. Aperture is very wide. I mean, I think this is a common this is, you can understand this from your daily experience also. So for example, when you are trying to read a book, right, which is in front of you, you sometimes need to dilate your pupils. You will see that your pupils are dilated, right? Dilation means what? The pupils are what? Basically, they are the aperture to the lens. Now, dilation of pupil means the aperture of the lens increases, allowing more amount of light to enter into your lens, into your eyes. But when you are trying to look at a very far distance, which is very far away from you, you normally tend to, contract your pupils. You try to look like this, right? Why do you do that? You need to lower the amount of light entering into your eyes by contracting your pupils. This is precisely the reason when the f number is low, that means the lens aperture is very high, then the depth of field is also very low. Only the nearest object you will be able to see, or the camera system or the optical system will be able to focus sharply. But as you increase the f number, and the aperture also reduces. When increasing f number means aperture is reducing, lens aperture is reducing. When you increase the f number, then you can see that the depth of field is also increasing. That means increasing f number basically increases the horizontal distance till which your optical system, your camera, can sharply focus on particular objects. In this case, you see, when the f number is very high, the object which is placed farthest away from the camera has also been portrayed or also been photographed very sharply. That means increasing an f number will increasing the depth of field, right? This is another very important issue that here. But you see, depth of field is inversely related, actually inversely related or inversely proportional to the focal length of the lens system. These two things are very important to understand over here, right? Next is another important thing, which is I was talking about repeatedly before. This is basically known as the circle of confusion. Now, in photography, the circle of confusion diameter, so as I told you, it's basically the diameter of the circle. You will understand why it is called circle. This diameter is often defined as the largest blur spot. Blur means hazy, not very sharp. Blur spot that will still be perceived by the human eye as a point when viewed on a final image from a standard viewing distance. The circle of confusion limit can be specified on a final image, for example a print, or on the original image on a film or image sensor with this definition. The circle of confusion limit in the original image can be set based on several factors. Number one, visual acuity. For most people, the closest comfortable viewing distance is around 25 centimeters. Right? Now, the distance at which we normally read a book or a magazine, whatever we are reading in front of us, we normally tend to place it at around 25 centimeters away from our eyes. At this distance, a person with good vision can usually distinguish an image resolution of 5 line pairs per millimeter. This LP per millimeter, equivalent to a circle of confusion of 0.2 millimeter in the final image, right? So that means what? To put it very simply, if you hold a book containing an image at 25 centimeter away from your eyes, then and that particular image has got a resolution of 5 line pairs per millimeter. That means in per millimeter distance there are 5 lines like this. All right. If this is 1 millimeter distance, then in this 1 millimeter distance there are 5 vertical lines and 5 horizontal lines like this. All right. So if that is the case, if you are reading or you are viewing an object or an image which is printed on a book or anything which is having a resolution of 5 line pairs per millimeter, then the circle of confusion is basically 0.2 millimeter. That means your optical system, your eyes, the optical system that can distinguish or identify the farthest object, right, that is away from the eyes as a as a blur spot. That blur spot's diameter is basically 0.2 millimeter. All right. And second point is basically the viewing condition. If the final image is viewed at approximately 25 centimeter, a final image circle of confusion of 0.2 millimeter often is appropriate. Alright, a comfortable viewing distance is also one at which the angle of view is approximately 60 degree at a distance of 25 centimeter, and it often may reasonably be assumed that for whole image viewing, a final image larger than 8 inches by 10 inches will be viewed at a distance correspondingly greater than 25 centimeter, and for which a larger circle of confusion may be acceptable. Alright. Now, another important thing is the method using which circle of confusion is basically calculated. Circle of confusion, in order to calculate the circle of confusion, what you do is, it may be confusing a little bit, but this is a very simple formula, I assure you. The formula is viewing distance in centimeter, all right, divided by 25 centimeter. Why? 25 centimeter is a normal viewing distance. This divided by desired final image resolution, right, in line pairs per millimeter, right. Again, this divided by enlargement. So if you are magnifying the image, maybe the image is magnified twice. If you are not magnifying it, then the enlargement factor is 1, right. So for example, if you consider this, that your viewing distance is around 50 centimeter, then what will be the circle of confusion there? And your resolution is let us say you're having 5 line pairs per millimeter, and you are magnifying the image that you are viewing has been magnified by 8 times. Then what will be the value of the circle of confusion? As you can see in front of you, that the value will be 0. If you do this, that is 50 divided by 25 is 2, 2 divided by 5, that divided by 0.4, 0.4 divided by 8 is 0.05. Alright, so this will be the value of circle of confusion. Okay. Now, to put it simply enough, so let me try to, because now we have seen the mathematical interpretation of the circle of confusion, let us also try to understand the physical significance of circle of confusion and the effect that aperture size, lens aperture, we do not use the term aperture and size together, I'm sorry. Aperture itself is sufficient enough to explain what I am trying to say. So, circle of confusion, so let me just try to draw one thing for you. So assume that this is a point source of object, okay, and this is the focal plane, right. Now what is the focal plane? In case of process camera, the focal plane basically should consist your duplicate transparency film, or in case of a camera, it is the plane in which basically your sensors are placed, right. Now in between both of these, that is your focal plane and your point source of object, which is basically the original, there is something which is known as a focusing element. Normally focusing element is what? The lens, right. Now in reality, even in our case also, process camera also, we do not use a single lens, we use a multiple lenses, because one lens is never enough to focus the image of the object or point object into the focal plane. So we use a multiple or a combination of lenses. So let us keep it in a simple discussion over here. Now you see, the place or the position of the lens will basically determine whether the light ray that is emerging out of this point source will actually fall onto the focal plane or not. Now, if let us say the the lens is actually placed very close to the point source or the original, right? Then instead of focusing the refracted light rays, the lens will actually create the image of the object somewhere before it, right? Somewhere before the focal plane, so we will not be able to see the image properly, right? Now, if the lens is placed very far away from the object, then instead of, again this problem will happen. Why? Because instead of focusing the object on the focal plane, it will focus the, ultimately the object will not be formed as sharp, but it will actually form somewhere over here behind the focal plane, right? Because of all this, we need to precisely control the distance that the lens has from the source object, right? Now this can be, or we can control the distance between the focal plane and the lens also. So either way, you have to control the distance of the lens such that the light rays which are coming or emanated from the point source object, after getting refracted through the lens, ultimately reaches and falls very precisely onto the focal plane. But you see, this is actually easier said than done. What actually happens is, if this is the focal plane, then normally instead of, we want what? We want this, right? Sharp, very sharp object or very sharp image of the original to form on the focal plane. But this rarely happens actually. Okay, so let me just, okay, in the bottom side we can do. This rarely happens. What actually happens? It might happen so that the light ray can either merge beforehand like this, so the image of the object is falling just a little bit away from the focal plane, right? Or the other thing can happen, that is the light ray can fall behind or meet behind the focal plane, right? Now you see this particular area, see this particular area. So if you, since this is a cross section, if you see the frontal view of this, instead of this cross sectional view, we will be able to see this as a circle, basically a circle. Why a circle? Because you see, if the image is falling, if the light rays are falling before the, or meeting before the focal plane, right, that will also create a spot basically, because when light rays fall on a plane, it forms a circular spot. Naturally it forms a circular spot. This particular circle, which is which may actually occur when the light rays meet either before the focal plane or behind the focal plane, that circle is basically known as the circle of confusion. Why it is known as circle of confusion? So normally what we think, that our brain, will human eye is only able to perceive the sharpest image if the light rays meet precisely exactly on a single point, converge on a single point, which is a point on the focal plane. But this is not entirely true. There is actually a threshold region where if the light ray meets or converge in any point before the focal plane or behind the focal plane, within this circle, within this threshold circle, basically an area within the threshold circle, then our human brain is still able to precisely identify or understand that image to be a sharp image and not a blurred image. This threshold area is basically known as the circle of confusion. Okay, I hope in the first part I explained the mathematical understanding of it, the analytical part, and now I explained the physical significance of the circle of confusion. Hope it is clear. Now here also you can see, so basically these are the different spots. Okay, so this is a spot that has been created when the light ray is meeting behind the focal plane. This is the precise sharp spot, and this is the spot which are actually, which is basically obtained when the light rays are meeting before the focal plane. In both the, all these cases, basically keeping this apart, actually in both the cases our brain instead of considering these things, that is situation 1 and situation 2, instead of analyzing these blots or these spots 1 and 2 as blurred, our brain will actually consider this to be sharp objects or sharp images. Because why? The light rays has met at a point behind the lens or before the lens within the circle of confusion, and our brain is tricked into thinking, okay, it is still within focal range only, it is still the object has formed, or the sorry, not the object, image has formed in the focal plane only. So this area in which our brain is tricked into thinking that an image which has not particularly formed on the focal plane, but yet our brain is perceived into thinking that that object, or sorry, that image is still sharp representation of the object, that circle or that area or that diameter is basically known as the circle of confusion for optical systems. Alright, I hope this is clear. Next, now let us start, because now we have, another thing I forgot to tell, that is, you see, this circle of confusion has got a very interesting relationship with the lens aperture. When the lens aperture, if you see in this situation, when the lens aperture is this much, then the circle of confusion is, let us say, maybe of certain diameter, maybe x1 diameter, x1 mm diameter. Okay. Now, if somehow the lens aperture is reduced to this much, then the circle of confusion is actually increasing in diameter. That means x2 will be greater than x1. So lens aperture and circle of confusion diameter are inversely related to each other. By decreasing the lens aperture, the circle of confusion increases. So when you are reducing the aperture, that means you are increasing the f number. So as soon as I am saying aperture, then the concept of f number comes back. So as soon as you are decreasing the aperture, that means you are increasing the f number. If you are increasing the f number or reducing the lens aperture, then the circle of confusion actually increases. So f number is directly proportional to circle of confusion, and lens aperture is inversely proportional to circle of confusion. This is also something which is to be kept in mind. So it will increase basically. Alright, so hope this is clear. Next, what we have is basically we will now start our discussion on the halftone theories of halftone photography. Basically, the picture this I have taken from, I think it's a very nice schematic, which nice picture. This is basically the representation of the Chinese philosopher Mo Tse, who is a 1st century AD philosopher in China. He first created this concept of camera obscura. Camera obscura is the first camera ever made, whereby, if you, I don't think you've seen those bioscope things that, or not the bioscope things, at least the small, in our childhood also we used to have these small cameras, and if you look through, it's not a real camera, obviously, it just had a shape of the camera. Inside there used to be a film, and if you look closely through that film, then those images that are there in the film, that would actually appear. So those are basically known as the pinhole cameras. Okay, the first such camera, known as the camera obscura, was created by Mo Tse. What he did was, he created this room, and he made a very, very small orifice in this one end of the room and covered the entire room completely, so that no light whatsoever could enter this room apart from through this orifice. What he saw was, and he put some people inside the room, and he did some poses, and the people inside the room actually saw an inverted image of the person. So this is actually quite understandable why light rays traveling are getting inversed, and that is why on this end we are getting an image of the original meaning this particular person is the original. Over here we are getting an image over on this side of the wall that is basically inversed in nature. So this was the first beginning of the pinhole camera, which was known as the camera obscura. Next, this is basically a schematic representation of pinhole camera. I think you can do this thing. You can create your own pinhole camera by taking a shoe box. You cover it with black art paper all through, and you just put a hole on one end of it and you place a a film on the other end. If you take out the film, if you expose the film through that small pinhole that you have made on the one end of the box, then light will enter and hit the film. If it's a light sensitive film, then that film will get exposed, and if you take out that film, you develop that film, you will be able to get the image, you will be able to get the photograph from that camera. So this is the concept of pinhole camera. Now so this is basically your schematic representation of pinhole camera. So you can do this experiment in the your home also. Just you can you take a shoe box, you cover the entire shoe box with black art paper all around, and you just poke a hole on one end, and on the opposite end you place a light sensitive film, and if you open the pinhole, and if you allow light to enter into the box pinhole camera and hit the photographic film, then the photographic film, because it's a light sensitive film, it will get exposed. If you develop it, you will get the image basically. Now the pinhole theory basically states that every point of the image that is obtained on the film transparency, in our case because we are using a process camera, even in the camera also, every point of the image that is obtained within the camera, that is obtained basically on the film placed inside of the camera, is a image of the lens aperture itself. So can you correlate the concept of lens aperture and pinhole over here? Why did I say this this particular way? Why did I say that every point in the image which is obtained on the film within the camera is basically an image of the lens aperture itself, right? So this point, every unique point that is obtained in the film which is present in the camera, it is basically an image of the lens aperture itself. So can you correlate between the concept of lens aperture and pinhole? Why am I saying lens aperture and not pinhole while saying the theory? Because you see, although there is no lens, you can just poke a hole using a pin in your shoebox camera and you will get the image, no doubt about it. But this opening, aperture means what? What did I say aperture? The meaning of aperture was, aperture means opening through which light enters. So in this case, the pinhole camera does not necessarily have a lens. It may or may not have a lens. And our process camera has got a lens, optical system. But ultimately the concept is same. Light is entering into the pinhole camera through that small opening, through that small pinhole, and light is entering our hitting the film which is placed on the ground glass in the process camera through the optical system, through the aperture, through that opening. In that opening there are some lenses present. That is the only difference. In pinhole camera there are no lens present. That is why, but that is still an aperture only. So what it means is, pinhole theory states that every point of the image that you are getting over here is basically an image of the lens aperture itself. Why? If I ask you, why is this true? Do you think this is true at all in the first place? Yes, of course it is true. You see, what is the source of light within this camera, in any camera for that matter? What is that area through which light enters into that camera? It is the lens aperture. That is the opening of the camera through which the light enters. There may be either lens, single lens, multi-lens system, complex lens system, whatever, or there may not be any lens like in the pinhole camera. But ultimately that is the source through which your light enters into the camera, isn't it? So that what basically this theory is stating, that this image is made out of innumerable number of images of that lens aperture. Alright, this image that you are getting on the film is made out of innumerable number of lens aperture in itself. Okay, so this is basically the pinhole theory of Halftone photography. Now there are other theories of halftone photography which I'll be talking about, but in case of the pinhole camera, you see the size of the pinhole increases with, or size of the dots, if you're using a halftone screen over here, not just transparency. If you place even a halftone screen, then you will get some halftone dots. Clear this up. Okay, now as you see that, as I already told you, that every point in the of the image that exists on the image is basically an image of the lens aperture itself. But you might ask me that where is that point you are talking about? Because if you are exposing a film without anything in between the film and the lens aperture, then that image is going to be a continuous tone photograph, right? So what is the point? Where are the points in the continuous tone photograph? Very good question. So in order to better understand the pinhole theory, what we do is we consider this in conjunction with halftone photography. We say that when we are placing a halftone screen in between the film and the lens aperture, then you get halftone image. Like this is, for example, the image that you're seeing in front of you now. This is basically a continuous tone image, right? Now, when you place a halftone image in front of it, what do you halftone screen in between the screen and the pinhole, then, or the lens aperture, then what is the nature of the image? You get an image which is broken down into halftone dots, right? Like this, like this. These are the halftone dots, right? Now if I say that ultimately these halftone dots together create the entire image that we want to reproduce, right? That I have already explained in the previous lecture. Now if I say reframe this pinhole theory by saying that every point in the image that we have got is basically an image of the pinhole or the lens aperture itself. Now does it make sense? Now do you understand where this point comes from? See, the halftone dots are basically the images of the lens aperture themselves. So it may be difficult for you to understand in terms of continuous tone images, because there are no such, it's true, there are no points in continuous tone. That is why it's known as continuous tone, that I have already explained in the first class. When you are talking about halftone photography, which is an image, halftone images are made up of innumerable number of halftone dots. So there are specific points. These points within the image, which actually makes up the entire image, are images of the lens aperture itself. This is stated by pinhole theory. Alright. Now you see, pinhole theory also states that when you are increasing the exposure time, the size of the dot increases. That is another thing. So if you are increasing the exposure time, the size of the dot will increase. But that is known as dot gain, that I have already explained in the previous class. But even if you maintain a very strict control over the exposure time, the dot gain will occur. Okay, there will be dot gain in the halftone image, the film that you are duplicating. That is why pinhole theory is not really sufficient enough to explain the reason why there is dot gain during halftone photography. We need some other theory to explain the logic or the reason behind why dot gain occurs during halftone photography. So in the next theories, there are two more theories which were promulgated. So one theory, the second theory basically, is known as the penumbral theory of halftone photography, and the third theory is known as the diffraction theory of halftone photography. Now you see why there are three theories. You might ask, if pinhole theory is not sufficient enough to explain the theory or the reason behind the dot gain, then penumbral theory must be sufficient enough. The answer is no. Penumbral theory is also not sufficient to explain the reason of dot gain. You can explain dot gain using penumbral theory when you are using a particular setting. So it is true for coarse screens, right? You can explain dot gain when it occurs in coarse screens. Coarse screen meaning resolution is very low. So for example, if I tell you 40 LPI screen and 160 LPI screen, which is having greater resolution? 160. That means LPI means what? Again, that explained already. Line pair per inch or line per inch simply in unit distance. In unit distance. So this is, if this is 1 inch distance, then there are basically 160 lines like this. This is one screen, right? And in the other screen there are only 40 lines per 1 inch. So whose resolution will be higher? In one linear inch or one linear distance, how, in which screen will we get greater number of halftone dots? Definitely the one which is being reproduced using a 160 LPI screen, halftone screen, right? Because its resolution is higher. So when we are using films having higher resolution, then another type of problem occurs. So in order to explain that type of dot gain, penumbral theory will not work. Penumbral theory will work when you are using coarse. So as I was saying, coarse screen means coarse is not your printing technology course, not that. Coarse is this spelling, coarse screen basically. Okay. So low resolution screen, these are coarse screen, and high resolution screen, these are fine. These are fine screens. So penumbral theory is sufficient enough to explain your dot gain, reason behind dot gain when you are using coarse screens. But when you are using fine screen, another type of problem occurs, which is explained by the diffraction theory of Halftone photography. That is why we have a total of 3 theories of Halftone photography. Alright, so this lecture, let it be this much, because these are a little bit, because these are all new to you. I want that you listen to them at a slow and steady pace, so that you develop these concepts very well, because this is going to be the bedrock on which you are going to develop the next concepts. If you do not understand what dot gain is, or what resolution is, or what is the cause of dot gain, you will not be able to understand tone reproduction, tone value increase, uh, tone response, and all these things, and how to calculate tone reproduction. All these things you will not be able to understand. So these are very fundamental concepts. I want you to listen. If you are not able to understand what I am saying by listening once, just go back, because you have the facility. Just rewind and listen once again. You will be able to understand. Okay. So let this lecture be till this much. I hope whatever I told you in this lecture is sufficiently clear to you. All right. Thank you for listening.